Hello and welcome to video number 2. This is part 2 of Calculus 1. Today we will be talking about evaluating limits. Last time when we left off, we had talked about the idea that the limit as x approaches c of f of x, say this is our f of x, and this here is our point where x equals c. What the limit was analyzing the behavior of this graph, seeing what this graph does as we get closer and closer to x equals c. So today, we'll be taking this knowledge, this idea of the limit, and we'll be applying it to various types of graphs and trying to solve for their limits. So today, we will be evaluating limits graphically and analytically. We will talk about properties of limits, one-sided limits and continuity, and infinite limits and asymptotes. And then next week, we will start covering the limit definition of the derivative. So, let's start with a simple example that'll take us right from where we were last week. So, let's say we want the limit as x approaches 2 of x plus 2. Let's draw this graph. We've got our coordinate axis here. And the graph kind of looks like this. F of x equals x plus 2. We want the limit as x approaches 2. So here is x equals 2. So there's a couple of ways that we could very simply look at this. One of them is using a table, and one of them is using the graph, looking at it graphically. Let's start by looking at a table of values. So as we said last time, this limit, in order for the limit to exist, it has to approach the same value from both the left side and the right side. So we're going to need two tables of values. One here for approaching from the left, and one here for approaching from the right. So let's say from the left, as we're approaching 2, we have 1.8, 1.9, 1.99, and 1.999. As you can see, each step, we're making our x closer and closer to 2. Now from the right is from this side of the graph, so from above 2. So let's say 2.1, 2.01, and 2.001. So these are our values. Now let's plug them into our equation to see what we get. So 1.9 plus 2 is going to be 3.9. 1.99 plus 2 is going to be 3.99. And 1.999 plus 2 is going to be 3.999. Now, that's from the left. It appears to be getting closer and closer to x equals 4. Now let's look at it from the right side. 2.1 plus 2 is 4.1. 2.01 plus 2 is 4.01. And 2.001 plus 2 is 4.001. So from the left, we're getting closer and closer to 4. And from the right, we're getting closer and closer to 4 as well. So we can say that the limit as x approaches 2, if x plus 2 is equal to 4. Now the other really simple way that we can do this is we can look at the graph of x plus 2. So we start here at the point 0, 2. You know the slope is 1, so the next point is 1, 3, We know what the next point is here, 2, 4. So we can look and say that this is defined here, and it's a continuous function, which we'll explain. We will define what a continuous function means later on in the video. But it is approaching this from value from both sides, and we know what the value is. So we can get to this conclusion by the same logic, or with graphical logic. Now, let's say we were given a function, limit as x approaches 2 of x times x minus 2 over x minus 2. So, if we were to look at this graph, and I'll keep the table of values here because we'll be using this again for this example. We look at this graph and see that this graph here looks like this. That should be going through the origin, not just above it. Crosses at the point 0, 0. And it goes up through here like this, but what is f of 2? If we plug 2 in, we get 2 times 2 minus 2 over 2 minus 2, which is equal to 2 times 0 over 0. Uh-oh. Well, we can't have a 0 in the denominator of the fraction. This here is undefined in terms of drawing this graph. So this graph does not have a point. There is no point on the graph at x equals 2. So this has a discontinuity at x equals 2. But if you look at the graph, it is approaching, it looks like it's clearly approaching a value from this side and this side. So let's take the limit. Let's try to take the limit of this function, f of x, as x approaches 2. So let's plug in our values. So at 1.9, we get 1.9 times 1.9 minus 2 divided by 1.9 minus 2. Those cancel. We get x equals 1.9. At 1.99, we get 1.99. And at 1.999, we get 1.999. So the graph from the left looks like it's getting closer and closer and closer to 2. Now, we also need to see what it's approaching from the right side in order to determine whether or not the limit does exist. So from the right side, we plug in 2.1, we get 2.1. We plug in 2.01, get 2.01, and if we plug in 2.001, we get 2.001, and it looks like from the right side, we are also clearly approaching 2. So in this case, we can say that the limit of this function as x approaches 2 is in fact equal to 2, even though the function isn't defined at x equals 2. But since we can see what its behavior looks like, what is it? It's getting closer and closer and closer to a single value as it gets closer and closer to that point from both sides. We can say that if there was a point there, then this is what the value of that point would be, is essentially the basis behind this limit. Now, if you want to, you can go and plug in these values into here. If you don't believe me, but the x minus 2 and the x minus 2 will cancel and you get this is equal to x, as long as x is not equal to 2. So if x is equal to 2, we get a defined value of 2 here, whereas we get an undefined value for this function. So x cannot equal 2. So let's move on. That's a brief review of evaluating limits graphically and with the tabular method. Now, let's move on to another example. This one's interesting as well. Let's say we have a piecewise function, f of x. And then after this example, we'll get into properties of limits and analyzing them, or solving for them analytically. But this is one more cool, important example. Let's say we have f of x equals x minus 2 over x minus 2 everywhere as long as x is not equal to 2. And we have 0 when x equals 2. So what this function looks like is this here, x minus 2 over x minus 2, is going to be 1 everywhere except x equals 2, but there is going to be a discontinuity there. But this is what this first part of the function looks like. As you can see, since it's for everywhere x is not equal to 2, it does not have, this portion of the graph does not have a value at x equals 2. This function, though, does, because we did say that at x equals 2, f of x is equal to 0. So this is the actual defined point at x equals 0. So if you were to look at this and say, all right, we want the limit as x approaches 2 of f of x, and just say, well, what is f of x? Because that's what the limit is f of x. You'd end up with this equals 0, and that's not correct. You can't just do that. And the reason is, if you look at this graph, from the left and from the right, we see that at 1.9, the value of the graph is 1.99. The value of the graph is also 1. 1.999, the value of the graph is 1. That for 2.1, 2.01, 2.001, the value of the graph is also 1. So we look, and as we approach x equals 2 from the left, it looks like it's approaching 1, and it is the same from the right. So if the graph from the left and the right is getting closer and closer and closer and closer to 1, as it's at 1, as we're getting closer and closer and closer to x equals 2, the limit is x approaches 2 of f of x would equal 1. In this case, it has absolutely nothing to do with this defined point here, because there's no behavior in the graph that would lead you to x equals 0 aside from its defining. So we can learn something very important from this, is that the limit of a function is not always going to be where the function is defined. And we'll see this more when we get to one-sided limits a little later. I'll do some more examples with piecewise functions and one-sided limits. But for now, let's move on to evaluating limits analytically. Let's get into some more analytic methods. So the first thing I'm going to talk about is the properties of limits. So limits have various properties. I will draw them out here. First one of these is the limit is x approaches c of a times f of x, where a is a constant, is equal to a times the limit is x approaches c of f of x. Property number 2. the limit is x approaches c of f of x plus or minus g of x. So if you have a composition of functions, this is equal to the limit is x approaches c of f of x plus or minus the limit is x approaches c of g of x. Our third property is that the limit is x approaches c of f of x divided by g of x. And this one here is a really nice one, especially compared to the quotient rule with derivatives, which we'll get to in a little bit. Not in this video, but in a future video. But for the limit, we have limit as x approaches c of f of x over g of x is equal to the limit as x approaches c of f of x over the limit as x approaches c of g of x. And our fourth property is that the limit is x approaches c of f of x times g of x is equal to the limit as x approaches c of f of x times the limit as x approaches c of g of x. And property number 5, limit is x approaches c of f of x to the n is equal to the limit as x approaches c of f of x raised to the n power where n is also a constant. So these are the 5 properties of limits. So I'll give you a minute. If you probably want to write these down. If you want to write these down, pause the video here, write them down, and then I'm going to continue with another problem. In order to do that, I'm going to have to erase these properties here. So if you want to write them down, pause the video, and write them down, and then play it when you want to start watching the examples. And if you want to try the examples by yourself, especially later on, then feel free to pause the video, try the example, and then keep watching to get the solution. So, I'm going to start with a couple of intuitive examples to show you that these properties work. Let's start with the limit. As x approaches 2 of x plus 3, we look at x equals 2. Graphically from the left and from the right, this function looks like it is approaching y equals 5. So we saw from the product of the addition of functions that limit as x approaches c of f of x plus g of x is equal to the limit as x approaches c of f of x plus the limit as x approaches c of g of x. Let's apply this here. The limit as x approaches 2 of x plus the limit as x approaches 2 of 3. Now the limit as x approaches c, this is another little important an important rule here of a constant, say a, this will always be equal to a. Because what you've got is a straight horizontal line, and you pick a point, let's say x equals c, from the left and from the right, that graph is approaching the value a at x equals c. So when we get here, as we look, if the limit as x approaches 2 of x is 2, plus the limit as x approaches 2 of 3 is 3, and this gives us 5. Now you may be wondering how I solved this one. Some of you may know already, may have figured it out without looking at a graph. But one of the ways that we can solve limits sometimes is by direct substitution. And what this means is that if you've got a graph like this, where f of x is continuous, you can see that anywhere you choose any point, let's say point x equals b, the limit from the left and the limit from the right will approach f of b. This here is f of b. Here at x equals 2, the limit from the left and the limit from the right both approach y equals 5. So for this, we could directly substitute the 2 into here and get 2 plus 3 is equal to 5. The problem with direct substitution is there are cases in which direct substitution doesn't work, and that's where we need to try out a couple of analytic methods to solve for those limits. So let me start with an example of that. Let's say we want to take the limit of, as x approaches 0. Actually, let me write this a little smaller and up here so that I can draw the graph. So we want to take the limit as x approaches 0 of sine squared x divided by sine of x. If we wanted to just try direct substitution here, and we look at this graph at first glance, you plug it into your graphing calculator, it looks like a sinusoidal function. So you say, all right, let's try direct substitution. Sine squared of 0 divided by sine of 0 is equal to, and we run into a little problem here. The sine of 0 is 0. So we get 0 squared divided by 0, which is 0 over 0. Earlier we said this is undefined when it comes to a graph. But when it comes to limits, we call anything in the form of, say, 0 over 0, or infinity to the infinity, or infinity to the 0, or infinity over infinity. We call values like this, or forms like this, we call them indeterminate forms. Essentially, what that means is that the 0 over 0 tells us that there is a limit, but directly substituting into this doesn't give us that limit. So let's think about this. Is there a way that we could, say, simplify this function now? Because if you look at this graph close up, there is a discontinuity here. It is undefined at this point. But this graph, so we have limit as x approaches 0 of sine of x over sine of x times sine of x. And if you look here, this will cancel. And at this point, I do have to set my domain. So, and the reason for this is because sine of pi is also 0, sine of 2 pi is also 0, sine of 3 pi is 0, sine of 4 pi is 0. So I'm going to say that pi is less than x, which is less than pi. Or, sorry, negative pi is less than x, which is less than pi. So we only have one point at which we get the indeterminate form 0 over 0. So over this domain, we see that if we plot the graph of sine of x over this domain, it looks exactly the same with one minor difference. That function is defined at x equals 0. So what we can do is, if we have a function p of x is equal to f of x, so if the two functions are equal at all x relatively close within a domain, within a is less than x, which is less than b, which is saying that as long as it is equal to this within some domain in which a is less than c is less than b. So what this is essentially saying is that if this function equals all x, let me finish the statement, except that x equals c, then limit as x approaches c, f of x is equal to limit as x approaches c of p of x, which is equal to p of c. Now, what this statement is saying is if we can find a function, if we can, in a sense, simplify this function to the point where we have a function that, relatively close to c, is equal at every point to the original function except at x equals c, well, we know that the behavior of the original graph, if they're completely equal except at x equals c, versus the behavior of the new graph as x approaches c, will be the same, because aside from at x equals c, they are the same. So they would approach the same value at x equals c, meaning that the limit as x approaches c of f of x is equal to the limit as x approaches c of p of x. And p of x is oftentimes going to be a function that is defined at x equals c. In this case, we change this here to limit as x approaches 0 of sine of x. Sine of x is defined. It's 0. Sine and sine of 0 is 0. So this here, sine of x, is our p of x, while sine squared x over sine of x is our f of x. So we can see that the behavior, as x approaches 0 to the left and x approaches 0 to the right of this graph, it's getting closer and closer and closer to the same value that this function is, except this function is defined. So we can simplify it down to this function, and then we can use direct substitution here. So we get that this is sine of 0, which is equal to 0. Meaning we can say that the limit as x approaches 0 of sine squared of x over sine of x is equal to 0. So this here, this one general rule is the basis behind a lot of solving limits analytically. So I'm going to run through a few examples here to make it a little easier to understand. Feel free to pause the video, try out the examples for yourself, and then come back and watch to get the answers. Or if you want to just continue watching. It's fine by me. So, let's try the limit is x approaches 2 of x squared minus 2x over x minus 2. Now, let's start by trying direct substitution, see what it gives us. So we say 2 squared minus 2 times 2 over 2 minus 2. So 2 squared is 4, minus 2 times 2 is 4, over 2 minus 2, which is equal, well, it's a 0 over 0. So we get an indeterminate form here, meaning we need to find a function p of x that is equivalent to f of x on a domain that contains c. So from a point before c to a point after c, both functions equal each other. So let's draw a graph of this function. And it helps if you're working with a limit or something like that. If you're given a function, it helps to draw the function. That way you can see better what you're trying to do, and you can check yourself better. So if we look at this function, we actually see that it looks like this, and there's a discontinuity. So let's try to simplify this function. What we want to do is we want to try to get to a point where we aren't going to get something that's divided by 0. And how can we do that? We can find an equivalent function that doesn't have an x minus 2 on the denominator. So in this case, let's try factoring the numerator out and see if it'll give us something that can cancel. So right from the get-go, we can factor out an x, see what that does. In parentheses, we have x minus 2. If you were to distribute that back, you get x squared minus 2x divided by x minus 2. When you look at that, we have two parts of a function that can cancel out. So we cancel that, so we get that our p of x is equal to x. Now, if we were to graph p of x equals x, we would see that actually over their entire domain, except for x equals 2, these two functions are equivalent. So we can say that the limit as x approaches 2 of f of x is equal to the limit as x approaches 2 of p of x, which is equal to p of 2. In this, we can directly substitute 2 into and get an answer that is not in an indeterminate form. P of 2 is equal to 2. Therefore, we know that the limit as x approaches 2 of x squared minus 2x over x minus 2 is equal to 2. Even though the function itself isn't defined at 0, the behavior of the graph, we can generally tell what the behavior of the graph is at that point. So let me do another example, put another one up on the board. And this is a method that one of the two methods, or one of the two big methods that we use to calculate limits analytically. We do limit as x approaches -3 of x squared minus x minus 6 over x plus 3. So here's the limit that we've got. Let's start by trying direct substitution. See if this works. So we get -3 squared minus -3 minus 6 over -3 plus 3 is equal to 9 minus -3 is +3 minus 6 divided by -3 plus 3, which is equal to 6 over 0. So this here, 6 over 0, is not an indeterminate form. If you get a function, like an answer that is a number divided by 0, you just say that the limit as x approaches -3 of this function does not exist. Or because there isn't a way to simplify this down to get an actual limit. So now let's try limit as x approaches -3 of x squared plus x minus 6 over x plus 3. So here we see this becomes a +3 instead of a -3. And we end up with this equaling 9 minus 9 over 3 minus 3, which is equal to 0 over 0. This is an indeterminate form. So what we have to do now is we have to simplify this graph. We have to try to find an equivalent p of x that we can use to evaluate the limit. So let's start by trying to factor out the top. Because what we want to do is we want to get rid of the x plus 3 on the denominator. So we start by saying x, and a reasonable way to go about this is say, let's say that x plus 3 is one of our factors on the top, because that would allow us to factor out x plus 3 on the denominator. And let's see if we can find something that would give us a factor of x plus 3 on the top. When we look in this case, we actually get that 3 times 2 is equal to 6. So 3 times -2 is equal to 6. And then positive 3x times plus negative 2x is 3x minus 2x, which is negative x. So this does equal this. This here is once again the limit as x approaches -3. And we can cancel these out to find our p of x is equal to x minus 2. And this here is another function that, if you were to graph it, would be equivalent to our original function f of x at every point except for x equals -3. So you look here, x equals -3, f of x has a discontinuity there, whereas p of x doesn't. So now, limit as x approaches -3 of f of x is equal to the limit as x approaches -3 of p of x, which is x minus 2. And let's try a direct substitution in this case. We get -3 minus 2 is equal to -5. So our limit here is -5. So more often than not, actually, whenever we get a graph that has that has a hole, right? That at one point isn't defined, but everywhere else around it is defined and continuous, is in this function here of x is undefined at x equals c, but the limit is x approaches c of f of x exists. Let's just say that this here is y equals. So let's say that the limit is f of x approaches c is equal to L. So the limit exists. And we know that if the limit exists, then the function approaches the same value from both the left side and the right side. What that tells us is that this is just going to be a little hole that we could, if we find an equivalent function by canceling something out, we could find a function that would serve to almost remove that discontinuity. So we call this type of discontinuity a removable discontinuity, because in doing the limit process, we were able to find a function that would be defined at that point and would have the same limit. So, let me just redraw my coordinate system, my little coordinate system here, graph. And let's work out another example. Limit. Try to lim is x approaches -5. And this one's a little more complicated. Pause the video, try it out for yourself. I would definitely recommend doing that. As limit as x approaches -5 of x cubed plus 5x squared plus x plus 5 all over x plus 5. So if we try direct substitution, let's try direct substitution. See if it is a continuous function now. So we get -5 cubed is -25 plus -5 squared. Oh no, that's -125. Sorry, so -125. -5 squared is +25 times 5 is plus 125. So these are going to cancel out. Plus x, which is plus -5 plus 5. Those cancel out over -5 plus 5. And would you believe it? We end up with another indeterminate form, 0 root. So what we want to do is we want to simplify this function down. We want to see if there's an equivalent p of x. So, sorry, I needed to grab a new piece of chalk. What we're going to do that is we're going to try to factor out the top. Now, this one isn't one that you're just going to be able to say x plus a times x minus b from looking at the x squared, the x, and the, like ax squared plus bx plus c, just factoring that. Because we have an x cubed, x squared, x, and 5. But how we can do this is we look, and we see, look at this part of the function here. We could take this and say that this part here is equal to x squared times x plus 5. If we distribute this x squared out, we get x cubed plus 5x squared. This part of the function here is plus 1 times x plus 5. Now, we can take this and say that this is x plus 5 multiplied by this and this, which is x squared plus 1. If you were to look at the distributive property, if we distribute this, x plus 5 to x squared, we get x squared times x plus 5. We distribute the x plus 5 to 1, we get 1 times x plus 5. So this here is this in factored form. So this becomes the limit is x approaches -5 of x plus 5 times x squared plus 1 over x plus 5. So now we see that these two can cancel, and we end up with our equivalent p of x equal to x squared plus 1. And if you were to analyze the domains of these functions, the only point at which they're not equal is x equals -5. So we can say that the limit, as x approaches -5 of our original function f of x, is equal to the limit as x approaches -5 of our new p of x, which is x squared plus 1. Now we try direct substitution, -5 squared plus 1, which is equal to 25, plus 1, which is equal to 26. And there is our limit right there, 26. Now, we'll go into one more method of solving limits analytically. This one is a little more difficult, a little more challenging, but you'll get the hang of it. And I might actually do a separate video on just more limit problems. But let's look at this one. This is rationalization. So we want the limit is x approaches 0 of square root x plus 1 minus 1 all over x. Let's say we were to try direct substitution for this. We'd say x equals 0, this is 0 plus 1, which is square root of 1. And the square root of 1 is 1. 1 minus 1 is 0, and x is 0. So this would give us 0 over 0, which is an indeterminate form. This is telling us that we need to go further. We need to simplify this somehow. But how would we go about simplifying this function with a square root in the numerator? We don't really know. I mean, we can't really just break it down into anything. But let's say we were to multiply the top by square root of x plus 1 plus 1. What would happen then? Well, using FOIL this, we get first, which is square root of x plus 1 squared. And if we want to multiply by this on the numerator, we have to multiply it by it on the denominator as well. And the reason for that is because this expression here is equal to 1. And we can multiply this function by 1 and get the same function. If we were to say multiply it by square root of x plus 1 alone, then we would be changing the function itself. But since we're only multiplying it by something that's equivalent to 1, multiplying anything by 1 spits back out the same thing. So this is going to become square root of x plus 1 squared plus square root of x plus 1 minus square root of x plus 1 minus 1 over x square root of x plus 1 plus 1. And this is the limit as x approaches 0 of this. Now we look, and why this is nice is when we square the square root, it cancels it out. So we get the limit is x approaches 0 of x plus 1. This here, the positive square root x plus 1 minus square root x plus 1, these cancel. And we have our minus 1 at the end, divided by x times square root of x plus 1 plus 1. In this here, if we simplify the numerator, we get the limit as x approaches 0. These cancel out of x over x times the square root of x plus 1 plus 1. Now these x's cancel out, and this gives us our equivalent function p of x. P of x is equal to 1 over square root x plus 1 plus 1. And these functions are equivalent on their domains whenever x is unequal to -1. And the domain of this function is actually -1 less than x, which is less than 0. So this function actually can't get any smaller than -1. But we have our c is 0, so that c does fit within this domain. So we can say that this limit, the limit as x approaches 0 of our f of x, is equal to the limit as x approaches 0 of 1 over square root of x plus 1 plus 1. Now let's try direct substitution here. See if our p of x is defined at x equals 0, or, yeah, see if this is defined there. So we have 1 over square root of 0 plus 1 plus 1, which is equal to 1 over square root of 1 plus 1. The square root of 1 we know is just 1. So this is equal to 1/2. And there is your limit for this problem. And what's so cool about this process is like it lets us analyze, lets us look at the behavior of graphs that where, say, a point doesn't exist there, we'd be able to see what it would be if it did exist. And the applications of the limit are really, really cool to see. So I have one more rationalization problem here before we move on. And that is the limit as x approaches 0 of 12 square root of x minus 3 all over x minus 9. The limit is x approaches 9, sorry, not x approaches 0. So, how do we solve this one? Well, we can start, if we try direct substitution, we'd get 12 times the square root of 9 is 3 minus 3 is 0, so it'd be 12 times 0 over 9 minus 9 is 0. So we get 0 over 0, an indeterminate form. Well, that's not good. We don't like indeterminate forms. They don't give us an answer. So what we have to do is we have to simplify this one. So how are we going to do that? Let's try rationalizing it. First thing, let's move the 12 out front. Since 12 is a constant, we can bring it out and slap it in front of the limit there. So 12 times the limit as x approaches 9 of square root of x minus 3 over x minus 9. And you look, we have a square root here. So it's probably a good idea to try the method of rationalization. We multiply it by square root of x plus 3. But in order to multiply by square root of x plus 3, we need to multiply the denominator as well. So we get that this is equal to 12 times the limit as x approaches 9 of, this becomes x, the minus 3 root x and the plus 3 root x cancel out, and negative 3 times positive 3 is negative 9. You get x minus 9 over x minus 9 times square root of x plus 3. These cancel out, and we get our equivalent p of x to be, so we get 12 times the limit as x approaches 9 of 1 over square root of x plus 3. And as long as we're on the domain 0 is less than x, which is less than infinity. So as long as x is greater than 0, and where this comes from is if you have, say, x is -1, square root of -1 is I, which doesn't exist in the real plane, the plane of real numbers. So we can say that as long as x is greater than 0, which will define this function and this function in the domain of real numbers. Our c is 9, so if that 9 does fit within this domain, in which these functions are equal at everywhere except for x equals 9. So we can try direct substitution here. So we get this is equal to 12 times 1 over square root of 9 plus 3, which is equal to 12 over 3 plus 3, which is equal to 12 over 6, which is equal to 2. So that is the limit of this function here. Okay, so now that we've gone through a few limit problems, understand limits a little bit better, hopefully you're starting to understand limits pretty well. I'm going to talk about one-sided limits and continuity. So now I drew my graph of f of x, and we wanted to know the limit of f of x as x approaches c. So right here, and I kept on saying that as as it approaches c from the left, and as it approaches c from the right, it has to approach the same value in order for the limit to exist. Well, the limit is just from the left and the right both combined if they approach the same value. But we can analyze the limit, or what the graph does from the left and what the graph does from the right separate. So if we want to analyze just what the graph approaches from the left, we say limit is x approaches c in a little negative sign there from the left, which if you see this negative sign, it just means as x approaches c from the left of f of x. And if we want the limit from the right, the limit from the right is limit is x approaches c, and there's a plus there, as x approaches c from the positive direction, which is right, of f of x. Now, one of the spots that this can be very, very useful is if you have, say, a piecewise function. So let's look at a quick example of this. Let's say you have f of x is equal to x. X is less than 0. 3 from 0 is less than or equal to x, which is less than or equal to 3, and then 2x. 3 is less than x. So if we want to draw this on a graph, we have, as long as x is less than 0, f of x equals x. So that looks like this. And you see it is not defined here because the domain is x is less than 0. It does not include x equals 0. Here, for x equals 3, 0 is less than or equal to x, so this one is defined at x equals 0, and it is defined all the way up until x equals 3. And we see that this is the second part of our graph. And then here we see 3 is less than x. So this part of the function isn't defined at 3, it's just defined after 3, is 2x So we want to plot this 3 times 2 is 6. So we draw a little circle here at 6 because it's not defined there. And then this here is our graph of f of x. So let's say we wanted to take the limit as x approaches 0 from the left of f of x. Well, the limit is x approaches 0 from the left of f of x. From the left, as it approaches 0, we're looking at the behavior of this part of the graph of x. And as x approaches 0 from the left, we get, so limit is x approaches 0 from the left of x, and the limit is x approaches 0 from the left. So that this is getting, x is getting closer and closer and closer to 0 as x is getting closer and closer to 0. The f of x is getting closer and closer and closer to 0. So we say that the limit from the left of this f of x is equal to 0. Say we wanted to take the limit as x approaches 0 from the right of f of x. Well, from the right, we're following along this line segment here, which is x equals 3. So this is the limit as x approaches 0 from the right of 3, and this is going to give us 3. Let's say we wanted the limit now for the other part that's discontinuous. Now these discontinuities are non-removable discontinuities, because as you can see, the limit doesn't exist. It approaches a different value from the left as it does from the right. And then the same here. So let's take the limit as x approaches 0 from the left, as x approaches 3 from the left. And as it's approaching 3 from the left, we're looking along this graph here, this part of the graph, which is 3, which is equal to the limit. X approaches 3 from the left at 3, and this equals 3. Say we wanted the limit as x approaches 3 from the right of f of x. So from the right, we're looking at this part of the graph here, which is f of x is equal to 2x. And the limit as x approaches 3 from the right of 2x is 6. Meaning, as we get closer and closer to 3 along the graph of 2x, we're getting closer and closer and closer to y equals 6. Now, earlier, I was talking about continuity. I'm going to erase our topics for today, the first 3 of them. We define a graph as continuous. F of x is continuous if 1, the limit as x approaches c is continuous. F of x is continuous at c if limit as x approaches c from the left of f of x is equal to the limit as x approaches c from the right of f of x. So what that's saying is that if they're both approaching the same value from the left and the right, then there's no jump discontinuity here if they're approaching the same value. So that's almost say if this, instead of being like this, were to be like this. They would be approaching the same value from the left and the right. The problem here is this doesn't always work out because here, say, this graph did look like this, but it wasn't defined at x equals 0. There's still a discontinuity there, meaning the function's undefined there, meaning it isn't continuous there. So we have another condition for continuity, and that is that the limit as x approaches c of f of x, which if the limit as x approaches c from the left is equal to the limit as x approaches c from the right of f of x, then we say that the limit as x approaches c of f of x does exist. If this is equal to f of c, then the function is continuous. Meaning, if this limit as x approaches c of f of x, is equal to the function at f of c. So if you look here at c equals 0, the limit exists. The limit right here is 0. But f of 0 is undefined, meaning this second condition for continuity is not met. So let's look at this example again. So we looked at the limit as x approaches 0 from the left was 0, and the limit as x approaches 0 from the right was 3. Does this fit our first requirement for continuity? Does the limit as x approaches c from the left of f of x equal the limit as x approaches c from the right of f of x? No, in this case it does not. Meaning this right here, the graph, is not continuous. When we look at the same case here, the limit as x approaches c from the left of f of x at x equals 3 is not equal to the limit as x approaches 3 from the right of f of x. So we say that this here is not continuous. Now let's say that we were to change this 3 to a 0, where 0 is less than x, which is less than or equal to 3. So this here goes down here. So this boundary here, less than or equal to 3, means it's still defined, x equals 3, but here 0 is less than x, meaning x is not defined at x equals 0. So we didn't, all that we changed was this. So all that we need to change is these two limits, the limit from the right and the limit from the left. This here, we changed our 3 to now 0. So it's the limit, this one here is the limit as x approaches 0 from the right, which is the limit as x approaches 0 from the right of 0, which is equal to 0, and as x approaches c, the limit from the left is the limit as x approaches c from the left of 0, which is equal to 0. So now we're looking to see if this function is continuous right here. Let's look at our first requirement. Is the limit as x approaches 0 from the left equal to the limit as x approaches 0 from the right? Yes, in this case it is. They're both equal to 0, meaning we can say that the limit as x approaches 0 of f of x is equal to 0. Now let's look at our second case. Does the limit as x approaches c of f of x equal f of c? Well, what's f of 0? We look here, it's x if x is less than 0. So 0 is not included in that range. So we go up to the next one. 0 is less than x, which is less than or equal to 3. 0 is not included in that range either. So 0 is not included in either of these ranges, meaning f of 0 is undefined, meaning this function is not continuous. Now let's say we were to say that this, say we were to get rid of this and say 2, f of x is 2 at x equals 0, and then I'll just expand this. 2x, 3 is less than x. So now we've got x equals 2. The limit from the left and the limit from the right as x approaches 0 don't change. So we still have that the limit as x approaches 0 of f of x is equal to 0. So we still satisfy the first requirement. Let's look at the second requirement. Limit as x approaches c of f of x is equal to f of c. But now we look at f of 0. we have f of 0 is equal to 2, because it says it right here. It's 2 when x is equal to 0. So yay, looks like we're all good. But if you look at the graph, this point is up here. This here is a discontinuity, right? So this function can't be continuous over at x equals 0, because this here, where it's defined, isn't where the limit is. Or case number 2, the limit as x approaches 0 of f of x is equal to 0, which is not equal to f of 0, which is 2. Now, if this were instead to say 0 is less than or equal to x, which is less than or equal to 3, that would define the function that x equals 0, and now f of 0 is 0, limit as x approaches 0 of f of x is 0, meaning this function would now be continuous right here. So those are one-sided limits and continuity. We will use one-sided limits a little more in our next section, which is infinite limits and asymptotes. So, start off, let me draw the graph of f of x is equal to 1 over x. So what does this graph look like? Well, let's say we want to know the limit as x approaches 0 of f of x, which is the limit as x approaches 0 of 1 over x, right? So let's draw a table to do this for us, because this one is, you look, we end up, this limit actually, if we were to just try direct substitution, we see that the limit itself would be 1 over 0. So the limit itself doesn't exist. So let's try a one-sided limit. Let's try the limit as x approaches 0 from the left of 1 over x. So that means we're approaching from the negative side over here. So let's say we've got negative 1, negative 0.1, negative 0.0. So 1 over negative 1 is negative 1. 1 over negative 0.1 is negative 10. 1 over negative 0.01 is negative 100. So if you look at this, it appears to be decreasing without bound, or it appears to be approaching negative infinity. Negative 1, negative 10, negative 100, negative 0.001 would be negative 1,000. And if you look at the graph of 1 over x, this is in fact what this graph appears to be doing. It looks like it's just going down, decreasing without bound. So we say that the limit as x approaches 0 from the left of 1 over x is negative infinity. Meaning, if this, as x approaches 0, keeps decreasing without bound. Now let's say we wanted to know the limit as x approaches 0 from the right of 1 over x. So we just change this. So let's use our same numbers, 1, 0.1, 0.01. So 1 over 1 is 1. 1 over 0.1 is 10. 1 over 0.01 is 100. This, on the contrary, from the right, seems to be increasing without bound. When you look at the graph of f of x equals 1 over x, that doesn't appear to be what it's doing. So we can say for this limit as x approaches 0 from the left of 1 over x is equal to negative infinity. Limit as x approaches 0 from the right of 1 over x is equal to positive infinity. As it approaches 0 from the left, it's decreasing without bound. As it approaches 0 from the right, it's increasing without bound. And we can say that if a function has a limit of positive or negative infinity as x approaches c, then it has a vertical asymptote at that point. So if limit as x approaches c from the right of f of x is equal to plus or minus infinity, or limit as x approaches c from the left of f of x is equal to plus or minus infinity, then f of x has a vertical asymptote at x equals c. So what a vertical asymptote is, or what an asymptote is it's essentially, it's a line that a function doesn't cross. So, or that, like, you look at a function, say you see 1 over x here, you keep going, let's say you keep going and going and going to, say, 50,000. 1 over 50,000 is a very, very small number, but it's not 0. In fact, if you look at the behavior of this function will never get to 0. It will get close, very, very, very close to y equals 0 as x approaches infinity, but it will never get there. So we say that this function has a horizontal asymptote at x equals 0, meaning it gets closer and closer to this value of x equals 0, or this value of y equals 0, but it never gets there. So in the same sense, we have a vertical asymptote, and we see that his limit as x approaches 0 from the left is negative infinity. Limit as x approaches 0 from the right is positive infinity. Meaning as we go closer and closer to 0, the function's increasing or decreasing without bound. It's never going to go and cross this vertical asymptote. So we say that it has, this function here has a vertical asymptote at x equals 0. So it has, a function has one of these asymptotes, a vertical one. The horizontal asymptote I will get into in a different video, but the function has a vertical asymptote at x equals c if the limit as x approaches c from the left, or the limit as x approaches c from the right of f of x is positive or negative infinity. So that's going to do it for today's video. This was a lot of information, a lot of limits. I think in a later video I will do more limit examples, but I'd also like to jump straight into the limit definition of the derivative. So we'll do that next time, the limit definition of the derivative, and then do some more limits examples at some point. But I hope you all have a great day. Hope you learned something new. If there's something that you're confused about, let me know in the comments. I can make a video on it or try to explain it to the best of my ability. So thank you for watching, and have a great rest of your day.